This video follows on from the video on current. In this video, I would like to talk further about the movement of particles such as electrons and ions, and also how to measure their movement. A metal can conduct electricity because of its metallic structure. The structure is made up of a regular arrangement of metal atoms, which we call a lattice. The outer shell of electrons becomes detached from each metal atom. In scientific terms, we say the electrons have become delocalized. So we leave behind a positive metal ion. So when we remove the electrons from the metal atom, we are left with a positive metal ion. These delocalized electrons form a sea of delocalized electrons in and around the positive metal ions. The sea of delocalized electrons are free to move or drift in the right conditions. In an electrical circuit, the electrons will flow from the negative terminal to the positive terminal. The reason for this is electrons are negatively charged and so are attracted to the positive terminal. Another way of describing current is conventional current. Conventional current is described as the flow of current from the positive to the negative terminal. And this definition applies for all types of charge carriers, whether they are positively or negatively charged. In general terms, current is always described as conventional current that flows from the positive to the negative terminal. However, if we look specifically at the particle, in terms of the particle, we can describe the current in terms of the charge that is moving. So if a positive charge is flowing, it will move in the same direction as conventional current. However, if a negative charge is flowing, for an example, an electron, then the actual flow of that particle will be in the opposite direction to conventional current. Okay, I now want to start talking a little bit about chemistry because it is here that we tend to see ions flowing. A good example of ions flowing is in an electrolyte. You may remember from GCSE chemistry that an electrolyte is a liquid which conducts electricity. A good example of an electrolyte is an ionic compound which is either molten, i.e. in its liquid state but hot, or when it is in an aqueous solution when it is dissolved in water. Ionic compounds are made up of positive and negative ions which are normally held together by tight ionic bonds. However, when the ionic compounds are in either their molten states or aqueous states, the ions are free to move. Since the ions have either a positive charge or a negative charge, when they move, they make an electrical current. Let's look at an example. Here we have a beaker full of aqueous copper sulfate solution. In the copper sulfate solution are two electrodes. Their job is to conduct the electricity from the solution to the wires. On the left-hand side, we have a brown electrode, the positive electrode. And on the right-hand side, we have a silver electrode, the negative electrode. The copper sulfate solution contains copper ions, Cu+, and sulfate ions, SO4 2-. Since the copper ions are positively charged, they will be attracted to the negative electrode, which is called the cathode. The positive copper ions are called cations because they are attracted to the negative cathode. At the cathode, the copper ions pick up an electron from the electrode to form copper solid. And we can actually write a half equation for what is going on at the cathode. Copper ions, aqueous or aqueous copper ions, Cu+, plus an electron produces solid copper, Cus solid, copper solid. The sulfate ions that are negatively charged are attracted to the positive electrode, which is called the anode. Therefore, the negative ions are called anions because they're attracted to the positive anode. The chemical reaction that takes place at the anode is slightly more complicated, and we will not be mentioning it in this video. Over the past two videos, we have said that a moving charge is a current. To measure a current, we use an ammeter. The ammeter is placed in a circuit in series with the components it is measuring. A good analogy is if we wish to measure the flow of wind, we would insert an anemometer, which is a device to measure wind, into the airflow. Since we wish to measure the flow of charge, we insert an ammeter into the flow of electrons. It is important for the ammeter to have almost zero resistance or negligible resistance, so the ammeter itself does not influence the current that it is measuring. Okay, so hopefully today I've gone into a little bit more detail on moving charges, particles and ions, and also explained briefly how we measure current. Thank you for watching. Please like and subscribe below. Thank you. Bye-bye.